All right, so this is a tutorial for how to simulate torsional stiffness with complete suspension in ANSYS. And so the first thing we're going to be doing is within Solidworks, we want to take our geometry and export it into a file type that ANSYS prefers. And so let's just start by opening up the assembly. So specifically for this tutorial, we're going to be simulating the FE6 chassis from Formula Racing at UC Davis. And so this was from, I believe, 2 years ago. We are currently working on the FE8 and FE9 chassis. And so this is the geometry. You can see the wheel package, the suspension, and the chassis is all in this assembly. And so for our purposes, we only need the suspension and the chassis. So we can actually just suppress everything we don't need. For example, the wheel package. These are just some empty folders. There were more components in this assembly that we don't need. So let's just suppress all of that as well. And all of this is probably fine. So we can go ahead, save as, and we're going to want to export it as parasolid binary. So that would be parasolid, then we just have to add the .x_b at the end of it. And so the reason we're doing this is parasolid binary has just been the most effective form. I've tried all of the other ones. I tried IGES, I tried STEP, parasolid text, that's what the T stands for, but some of them work, but parasolid binary has never not worked. So that's just what I always recommend. And so we can just call it fe6.x_b. And I actually already saved this to a folder here, but we can just override it. Let's replace that and just say, okay, resolve components. So just gonna go save. And we don't need to resolve the suppressed components. So we're all done with that. So we can go ahead, close SolidWorks, don't need to save anything. And now I have open ANSYS Workbench, and the only module analysis system that we're going to be working in is static structural. So we just drag and drop that into our workspace. And let's just start off by configuring our engineering data. The only material we're going to be using is 4130 steel. So we can get rid of this default structural steel that ANSYS puts in and go into our materials. And I have actually made a custom material library, which has 4130. We're just going to add that in. And if you're on our team, you can find this material library on the Google Drive. So yeah, and if we go back, we can see it has been added to our engineering data. And we can just go ahead and close this tab. So that's all done. Got that nice check mark. And so what static structural is, it's just the basic workflow that we need to follow in order to simulate our part. So we start with engineering data. What are our material properties? Which materials are we using in our simulation? Then we go into geometry. This is actually going to be probably the most tedious step. We have to pretty much convert the current geometry that we will import and make it in a form that is simple for ANSYS to compute. That'll make sense in a bit. And then the last tab is model. So actually model, setup, solution, results. This all happens within a single program, as we'll see. So this is just the basic workflow that we're going to follow within. It's called ANSYS Mechanical. So that's coming up soon. But first, just start simple. We'll go to geometry, import our geometry. Let's browse. So the geometry we want is FE6. This is what we just did. Open that up, and you can see the P for parasolid, and that's all sweet. And we can actually just save our project now, just so that we don't lose any progress that we make. Let's just call this FE6 torsion 1. And hit save. And now the entire Workbench file has been saved, and we're going to edit our geometry in SpaceClaim. So in the bottom left, we can see it's starting up SpaceClaim. So it might take a couple seconds, but not too long. And so what SpaceClaim is, it's basically a CAD tool that's built within ANSYS, and it's a lot more flexible than Solidworks or any of the standard CAD softwares. And I think the main reason for that is it's kind of funky. There's no constraints within ANSYS SpaceClaim. And so what that means is you can use a plane or something as a reference to do something, and if you delete that plane, the thing that you did with that plane will not be affected at all. It's kind of a weird concept. Like you can, it's really flexible. We'll see how all of that works. So yeah, you can get comfortable with just navigating ANSYS. I think the mouse controls are very similar to SolidWorks. There's a bunch of tabs. It's kind of intimidating at first, but we'll go through the tools that we do end up using. So first up, let's just do some housekeeping. We just want to clean up what we're looking at. We have all of these are just chassis parts. So we can just put it all in a folder so it's just easier to look at. So select all the orange block things. These are all the chassis beams, and we're gonna right click, move to new component, and usually doesn't take this long. Okay, there we go. So it's been moved to this component. Let's just call it chassis raw. And then we can do the same for all the suspension parts, which are in blue. Right click, move to new component, and let's call this suspension raw. And now if we minimize these two folders we just created, it's a lot nicer to look at. And like see if we uncheck the suspension, all of those go away. Uncheck the chassis. It's a lot easier to look at now. And let's see what we do next. So we have our chassis, all our chassis beams, and we're going to want to go to the Prepare tab, and we're going to extract. So it's going to, all right, I'll just show you. So just highlight all of the beams, and what it does is it basically converts it all into a bunch of lines, and each line is now a beam element within ANSYS. And so it's just a lot simpler to work with these beam elements because it uses like beam theory or something like that, which is just a lot more efficient for FEA. And so we can see, okay, so yeah, one question that might be on your mind is, weren't all the tubes different sizes? Like some were like different thicknesses and sizes and stuff like that? The answer is yes, they are, but ANSYS's software is smart enough to figure out what size, what thickness, what cross section is to be applied to each beam element. And if you go into beam profiles, you can actually see all the different profiles that each beam takes on. So for example, let's just take this random beam right here in the bottom, in the front roll hoop. This beam is extracted profile 1, which is this guy right here. And if we go right click, edit beam profile, we can, 1 second. This is actually interesting. It is, okay, yeah, sorry about that. I just needed to check something. So yeah, it does look like it's all good. This profile wasn't the best example. Let's see, okay, this beam here in the back, right here. Let's see what beam extracted profile 3 corresponds to. So if we go right click, edit beam profile, we can see this is the tube that is corresponding to that one beam. And if we go to measure, let's just see, what is the outer diameter? 12.7 millimeters. I just use a quick calculator. Millimeters to inches. Okay, yeah, half an inch in diameter. And what's the thickness? Okay, 12.7 minus 10.2. So 2.5 millimeters to inches. Okay, about 0.95 thickness, which I believe that's correct. That's what was actually assigned to this beam in Solidworks as a weldment. So yeah, with that, you can see there's quite a lot of different profiles that were used throughout the chassis, and ANSYS is smart enough to just figure out which beam corresponds to which profile, and it gets the profile correctly. So with that, another thing you might notice now is there's a lot of weird edges like this. Some of them aren't even connected, and there's a lot of gaps everywhere, and we don't want that for our simulation. So how do we fix that? There's a lot of tools built in right into ANSYS. I believe Connect is the tool. Yeah, so Connect is the tool we want. And if you go into the left here for options, let's make the max distance really large. Let's just make it 50 millimeters. So it's saying anything within 50 millimeters that isn't really connected is just going to be highlighted in red as something that needs to be fixed. And so the reason we start big and then go small, well, it'll become apparent as we do it, but it's mostly just to fix the big things first and then go more into the details afterwards. So if we start with just this corner, we click it, it fixes it, looks like a perfect corner now. So we can do that at all 4 corners. That looks good. It changes it slightly than what it originally was, but it's like this fixing this is more important. Like fixing the gaps is more important than having exact 100% accuracy, if that makes sense. Like this is an assumption, I guess, that we are making to the model, which is necessary to get better results, if that makes sense. So yeah, let's fix this corner, perfect. Do the other side too. Yeah, and it's a good assumption to assume whatever happens on this left side will also be the same on the right side. So like I'm going deep into this just to see what it looks like. Okay, this corner looks good. So I'm assuming that the other corner also would look good. I don't need to like zoom in and check everything like that, if that makes sense. So this corner we actually don't want to resolve because it's highlighting this and this, saying that, okay, these two things need to be connected, but that's not something we want. Like, look, if I do that, that is very wrong. We don't want that to happen. So it requires a bit of quality control, but yeah, it's just a little tedious, not too bad. We connect this guy. What is this? Okay. Same on the other side. Okay. And this is kind of a mess here. That's probably good. That's good. Let's see what happens there. That still looks good. And then good, good. Okay, yeah, we don't want to do that yet. We'll probably go finer in our max distance, and then we'll resolve this corner. Same with that. So we'll come back to this area. It's a little bit of a mess right now. This looks good. Looks good. Yeah, so it's just a little tedious, but it's not too bad. And we'll come back to that too. I just undid that. I'm not sure if we want that. That's good. 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 Okay. Don't need to do that. Great. So we got most of the major gaps. Let's see. Go to back view. That's actually pretty good. Sweet. Okay, so we just have some of the gaps that are difficult. We tried all of these. So now it's a good time. We got the big things all resolved. All the points that weren't connected earlier are now connected, except for a handful. All the like extra edges have been trimmed up into a nice clean corner. And now let's just go down maybe to, I don't know, let's see what 40 does. Okay. So we actually, yeah, in this corner particularly, we want to resolve this without connecting it with this, if that makes sense. See, if the bounding range, the max range is too big right now, that it's including this entire area as something that needs to be resolved, whereas we only want this part to be resolved without this. So let's see if it's still the case everywhere else. Yeah. So we'll go even smaller, 30. Perfect. So see, now we made it small enough so that it doesn't involve this extra little node. This is still something that doesn't need to be resolved together, but alone is good. Same thing here. Perfect. And now pretty much the entire chassis is all ready to go except these corners, which again require, ooh, that might actually be good. Let's see what happens when we go to 20. Okay, that's pretty good. What was 30 again? Yeah, we don't want that. So, okay, we're ready to go to 20 then. That's good. That's good. And then, okay, that's still a problem. All right, so now let's go down to 10. That is interesting. Nope. Yeah, I just undid that. So I'm basically just trying to see what looks right and then going from there. Undid again. Is there even a gap here that needs to be resolved? I don't think so. Let's go down to 5. Okay, there might be something there. Yeah. Ooh, there's a gap there. Okay, so maybe let's go back to 10. Yeah, sorry, this is the first time I'm doing this chassis too, so there's some things that I haven't worked out yet. Okay, so that actually might be the right move for this. So I went to 10 millimeters, and basically these two weren't connected, but now they are. And same thing here. Okay, I think it's all symmetric. Yeah. Okay, perfect. So I think our chassis is now all good. Yeah, I don't see any other ends that haven't been addressed. Okay, so that's it for chassis preparation for now. And now is more interesting part of uh, incorporating the suspension as well. So first off, I always just go back to the design tab and hit this check mark so that it's not in a specific tool. Like for example, if we were in Connect, like every touch is, like every time you click, it relates to the Connect tool. The select is just selecting. So it's nice to be in. So now let's pull up the raw suspension, see what it looks like. It's a little complicated, but it's not too bad. So one thing that's important here, so first just to go over the suspension like anatomy, we have the upper A arms, that's what these two are called, or also known as wishbones. This is the lower A arms. In FE6, this particular chassis, it's different than a typical like beam. They ended up using a plate here, which I mean, it's still called an A arm, lower A arm, but this is in the rear here is what it's typically looking like. So these are lower A arms, upper A arms. This is a push rod. So that's because when you apply a load upwards, it pushes, apply, the force goes through the push rod into the, this is the rocker, and then which goes into the spring. So A arms, push rod, rocker, spring. And same thing in the front, A arms, rocker, push, no, A arms, sorry, A arms, push rod, rocker, spring. And so you'll notice the configuration of the push rod is a little different in the rear and the front. In the front, it's connected to the lower A arm, and in the rear, it's connected to the upper A arm. That's just something to keep in mind. And another thing is in reference to a wheel package component, the upright, that's what connects both the upper and lower A arms. So an upright member will go right there and there in the rear. So, okay, this suspension as it is right now is more complicated than we want it to be for our FEA purposes. And so we actually are going to simplify it quite a lot, similar to how we simplified the chassis from like solid members to lines, which are represented as beams. So we're going to do the same thing, represent these guys as beams. And even this plate, I think the best way would be to keep this point, pick a point, but just represent it as a beam. That's an assumption that we're making, a simplification, but I think it's okay for our purposes. And another simplification is we're going to consider the entire push rod, rocker, shock configuration as just a simple single thing that connects to the chassis. And gosh, it's difficult to explain why we're doing this right now. I'll be sure to cover it in the next module. Yeah, when we get there, I'll explain what types of things haven't been solving for me as I've been doing these simulations, and why that kind of pushed me to make this simplification of condensing these three parts into just a single part. So yeah, we'll go through that in a bit. But yeah, so for now we're going to see how the power of space claim, where there's no constraints and super flexible with everything. So yeah, basically we're going to draw lines to the correct pickup points at all four corners. And yeah, we'll see how that's done. So first thing, let's just mark the upright A-arm points, these pickup points. Let's just mark the center of those. And the way we're going to do that is just create a point, and there's different ways to sketch. You can see like the plane is kind of but we're just going to do it in 3D mode, which is just with this button. And see, the plane goes away, and you can basically draw wherever the heck you want. And so right now, if we zoom into the A-arm end, we can see there's an axis here, and we just want to put it to the center of that axis. So we just want to drop a point there. I don't know if it's, I don't think it's creating the point. That's odd. Okay, there we go. It just took a couple clicks, but now you can see this curves tab has popped up, and the point that I created is right there. You can see it like highlighted in green. And so if we go to this like side view, we can see it is indeed in the center, or close enough at least. And we're going to make a similar point in the lower A-arm in the front. So I believe that is the center. And let's just make a point right there. So we have our points now in the front, and let's do the same thing in the rear. We're going to zoom in a bunch and try to drop a point right there. Perfect. And same thing down here. Let's zoom in and make our point. So we have all 4 points now. We also would like to make points at, or let's come back to that later. Let's just do what we're doing right now. So we can now go ahead and hide our suspension, and all we have now are points in the front and in the rear, and we're going to use these points to make our suspension. So again, we're going to draw a line in 3D mode, and we're going to start at the point to the node at which the A-arm is supposed to connect at, and same thing here. If you zoom out, it looks about right, what an A-arm should look like. And same thing at the upper A-arm. One there, and we'll actually notice there's not really a node where it should be connecting at. So let's actually create that node. And the way we're going to do that is we're going to split this curved curve. So just use the splitting tool, and we're going to say, okay, we want to split this curve into 2, and let's just choose the midpoint. So now we can see it's been split into 2. And now we have our node, 3D, click there, and at the node we just created, which is right there. And so now we can indeed see, oh wait, let me undo that. It didn't come out right. So one more time, draw our line at the node we just created. So yeah, we split this curve into two, and we're drawing the A arm from the node we created to this other node we created by splitting this line. And let's do the same split on the right side of the chassis. So use the split tool, and on this curve at the midpoint. And you can see here in the top left, it says it's snapped to the midpoint, which is perfect. Great. And yeah, we're actually just going to do it on one side, but mirror it to the other side. But still, the splitting curve is a feature that can't be mirrored. Or I guess it technically can, but it's just easier to do that yourself. And okay, the same thing here in the rear. I actually see more points. I'm not sure what this point, okay, just went away. But okay, so same thing here. Let's just start with the bottom one. So it looks a little bit easier. 3D mode, draw to there. I just hit escape to get out of the drawing, if that makes sense. Otherwise, like it's gonna make another line from here to somewhere else. But if you hit escape, you just you're still on the tool, but not from the last point, if that makes sense. And then just to check, okay, the top will connect to this node and this node. So let's just do that. Hit escape, and boom. So we're all done there. And now let's actually just connect these points. So we can connect them. This is just a beam representation of our upright. So right there. And so now the basic structure of our suspension is all done. Let's not mirror it just yet. Yeah, well, let's wait on mirroring it for a bit. So the cool thing about ANSYS, as we'll now see, we can delete these points, and nothing, like the lines that are referenced to that point, they don't go away. So which is really pretty sweet. It's a little bit interesting, but that's ANSYS for you, which is pretty cool. Okay, so now let's pull up the raw suspension again. Our approximations, they look pretty good. They're a little off, as they will be, but again, it's a model. Model will not be an exact representation of what's going on, but I think it's going to be close enough. So again, as I said, we don't need to create the push rod, rocker, or shock in the front because we're just going to consider it as direct acting. So it's just going to go as a spring member within the next module from here to the right pickup point. And that'll all make sense in a bit, but the important part now is we're done with the front. That's all we need right now from the front, but we're not done with the rear. So we're actually going to create this push rod and this rocker in the rear. And the way we need to do that is we already have the point at which the push rod should connect. Granted, in reality, it connects here, but we're just going to say it connects here. And now all we need is the point where the where the rocker connects to the push rod. And so, okay, the easiest way I've found to do that is to just create a plane. We're going to create it with multiple parts or references. So just click this button, click both ends of the rocker, and it automatically makes a mid plane. So if you click that mid plane, it gives it to you. And now on this plane, we're going to sketch a point. So I just click the plane, then I click the point, and now we are in sketch mode on a 2D grid, which is exactly what we want. And so if we go zoom into this, all we need to do, drop a point there and drop a point there. That's where the push rod and rocker connect, and this is where the shock and the rocker connect. And yeah, that's basically it. So we have our 2 more points for us, and we can delete this plane and the points will still be there. I just like keeping my workspace clean. Yeah, and so now let's again hide our suspension, the raw suspension, and we can draw a line in 3D mode from here to our push rod rocker pickup, and then another one from the push rod rocker pickup to the spring rocker pickup. So essentially, we now have drawn our push rod and also our rocker in the rear. And now we are basically done with the rear suspension, and we can delete these 2 points so we don't need them anymore. And yeah, it looks pretty sweet. All we need to do now is mirror all the suspension geometry, or the lines at least. They're not beams yet. We'll show you how to make them beams. And yeah, so to do that, we're going to create a plane with this plane button. And I just like clicking the coordinate system. It makes 3 planes about at each axis. And we don't need the, make sure to go back into select. So we don't need this plane or this plane. Yeah, I haven't been able to figure out how to make just this plane, so I go through that like process, but it's okay. So now we want to mirror about this plane, and we want to mirror all of these lines. So I'm just gonna click all the lines. This might not have been the best way to do it. Okay, the front is nearly there. Okay, what else am I missing? I'm missing this guy, this, and this. Okay, so now let's go ahead, delete our plane. And okay, everything looks good to me on both sides. So perfect. Now we have all the suspension geometry on both sides of our chassis. And just want to check something. Okay, we do have nodes for the spring, which we're going to use later, but yeah, don't worry about that yet. But okay, so now we have all our geometry. Now you're probably wondering, okay, these are just lines, so how do we represent these as beams? And that's a great question to have right now. And so the simple way is you just select which line you want to convert. You go to prepare and you simply click, okay, it's this profile, and it'll convert it into a beam. And so before we do that, let's actually see what beams okay, actually, I'm sorry. Let's clean our workspace up again. Let's move all the chassis beams. So I just clicked and then held shift and clicked this just to select all. And we're gonna move all of these to a chassis beam folder. Okay, and now that's all clean. And let's pull up the suspension and let's just see what profiles these correspond to. So if we go to the Prepare tab and click Extract on, for example, this guy, let's do it on this guy. Let's just check these two. Okay, so interesting. And this guy. Okay, so by the looks of it, all of the A arms are extracted profile 7, so as you can see here, and the push rods are extracted profile 9. So that's just how I see, okay, that's what they are. But we're not going to actually use, okay, this might be a little confusing right now, I understand. So we made some lines just now. So we're going to use those as our beams rather than using like these as our beams. And I'll go over this again. It might be a little confusing. So okay, let's delete these beams. The only reason we extracted these beams were in order to see what profiles the chassis, the A-arms had been configured in, the A-arms and push rods had been configured in within SolidWorks. So yeah, I'll go over that again. We can hide all our suspension, and we're going to click all of our, go into select, click all of our A-arms. Now that I'm thinking about it, it might have been a better idea to mirror after they were beams, but it's okay, just a little bit more work. Okay, making sure it's all selected correctly. Great, and so if we just recall what we did, each A-arm is extracted profile number 7. So just click that, and now the lines that we created are now beams, which is exactly what we want. And we can convert the push rods, so that's these two, and let's just assume that the rocker and push rod are the same thickness, which is obviously not accurate since the rocker isn't a beam, but we're just representing it like that. And I think it's a safe assumption to consider them to be the same extracted profile 9. Great, and then uprights, let's just say, are the same beams as our extracted profile number 7, same as the A-arms, which is another fine assumption. So now you'll see the curves folder, which contain all our lines, are now gone. So all of those lines have been converted into beams of the appropriate profile. And the way we found that profile was by actually using the original geometry and extracting this geometry just in order to see what they were configured as. And so now you might be wondering, okay, why did we have to draw the suspension ourselves rather than just use the raw suspension and just extract those beams and that's it? So the reason for that is you'll see there's a lot more complexity here than we want. Like we don't care about all this interaction here. If you'll notice in the lines that we created, it's all just like connected to one another. There's no like actual interaction here. There's no, it's a lot simpler. For example, like this isn't even connected to the point because there's actually a tab box that would go here to actually connect the this rod end to the chassis. And so like this is perfectly good for, this is correct for what we actually design and manufacture. But for the purpose of our simulation, we only care about the points to which the loads are distributed. And we want to make it as simple as possible. So you'll see an overlay of the lines that we ended up doing. They're not exactly the same angles and everything, but they use the same points. So this is like, I'd say this is the right way to do a simulation. And you'll see here too, like it's a little bit off, but we're making these approximations in order to make the simulation solve a lot faster and also just be as simple as possible, because like the simulation itself is pretty complex. So if we're able to save some complexity in the design of it or in the actual model, then that's just beneficial to us. It'll save computing power. It'll save our own headaches. We don't have to model like the whole like tab box interaction here. It's just directly connected. So it's just going to save us some time, some headache in the future. So, okay, now we are almost ready to go into the next module. So yeah, all of the difficult work has been done. And let's actually right click and suppress the raw files. So suppress for physics basically means it's not going to transport any of that to the next module, as that'll become more clear in a bit too. But okay, yeah, first things first, we have to, let's just categorize everything. It'll make our lives easier in the future. So I'm selecting all of the upper A arms. And we're just going to right click, move to new component. We can just call it uppers. Okay, now let's do the same for the lowers. Perfect. Move to new component, rename lowers. Let's do the same for upright. And finally, the push rods and rockers. Great. So now everything has been categorized. Before moving on now, something that I know already that needs to be done just since I've gone through this process a couple times is we want to create coordinate systems at the rocker, and this will become apparent why I'm doing this later. Okay, that looks good. Cool. So I just made 2 coordinate systems. And okay, now all that remains is we need to share to basically to this next module in Workbench. So we have to tell it what things are we sharing. So I guess the best way to do that is first hide everything except the chassis beams. We can hit share. It finds all of the vertices in the chassis. Hit check. So everything is looking all good. Actually, one second. Let's unshare this. I'm sorry. If you recall at the beginning, like I was looking at extracted profile 1, and I noticed that it was a solid beam, which I thought was pretty confusing why, but I think it's actually just an ANSYS error. And if you notice, like that turned blue just now when we shared it, because it's considering that as an edge rather than as a beam or as a tube. That's something we don't want, and let's just fix that manually. So it should be the same as what this profile, which is, what is it? Extracted profile number 5. So we're gonna just convert this guy to extracted profile 5. And are there any other ones? I know there's at least 2 more. Okay, maybe I'm just not seeing them right now. Okay, let's just see if this tells us anything. Still says 3 edges, which is interesting. Okay, I'm just going to pause this and try to troubleshoot so that it's not just wasting your time. All right, I am back. Sorry about that. So the way that I am going to resolve this is just by deleting these and redrawing them. That's probably the easiest way. This guy, we know it should be extracted profile 5, and this guy 7. So I'm just gonna delete 1. Did it delete? Okay, so that's gone. Just draw manually a line from there to there, and delete this guy. All right, it's not cooperating. There we go. Okay, so that's done. And same thing here. Okay, and so these two are extracted profile number 7. And this is number 5. Okay, and now we just have to put it back into the right folder. Okay, yeah, this is something I've had trouble with before too. So I might have to select all of the chassis beams and also the new beam, and then make it into a new component. It's just something, it doesn't let you move components into existing folders. You just have to make new folders, or at least I haven't been able to figure that out. So now delete the old folder. Okay, so now again, we are ready to share. And good, no more edges, it's all vertices, and everything's green, which is nice. So that's that. And now we're gonna do the same thing for the uppers and lowers. Hit share again, found our vertices, looks good. And so now, okay, this is something that is interesting. We aren't able to share anything without a vertice. So like, okay, if I try it, you'll see the error. There's no objects to share. So we actually have to develop our own vertices. So I'm just going to split each curve in the middle, which is perfectly fine. Okay, and now we'll share it, hit OK, and repeat with push rods. Okay, looks good. Share, check. And lastly, with rockers, splitting them. Okay. And again, we'll go to share, check. Okay, and now you can see everything is like it's a different color now. It has this like pink thing here. And so if we pull up all the geometry now, we'll see orange and green, which is what we want. And so, okay, you might be wondering, why do we have to split the components the way we did? Why can't we just pull up all the suspension and the chassis at the same time and share it all together? Because it already has vertices in that way. So the answer is you can. There's nothing wrong with that, apparently, but like the reason I've shared them separately is so that we can actually interact with each component on its own rather than having to deal with it as a single component. And you'll see why that's needed for the joint definitions that we are going to do. So yeah, if we share the entire thing at once, it'll only import it as a single like folder of parts. Whereas since we did it separately, we're able to interact with each component also separately. I'll make sure to stress that again or show you in practice where that is important. But yeah, let me just save this space claim file. Okay, all saved. Now we can just go ahead, exit this. We can always come back to it if I missed something. I might have missed something that I needed to do, but it's okay. So go into model now, next tab, we can see a nice, beautiful check mark there and hit edit. Now bottom left, it's starting ANSYS mechanical. So yeah, the overall process, it's just a little bit tedious, but it'll be, it's worth it. At the end, the simulation is pretty powerful. Like once it's all set up with the proper joint definitions and everything, we'll see like it's very easy to manipulate once it's set up. But the actual setting up, I wish there was a way to automate it, but there's just a lot of like quality control and subjective things that require a human, at least right now. So it's loading everything in. Okay, this is interesting. Okay, this doesn't usually happen. I'm gonna pause recording to troubleshoot. All right, yeah, so we're just gonna come back to this in a bit. I haven't been able to resolve that last issue. I'm gonna still keep working on it. Yeah, all the stuff that we've learned up till now is valid for a working simulation as well. I don't think we made any mistakes there. It's just some issue with the file type that we're gonna work on resolving before we continue recording. So yeah, stay tuned for part 2. Thank you.